Hello everybody, this is a video on Intro to Graphing Logarithms. Alright, these notes are being pulled from a shared doc that you all should have access to, so let's get right into it. Alright, the topic is graphing logs. To start talking about graphing, we always talk about the parent function. The parent function of a logarithm looks like f of x equals log of x. If you recall, whenever we don't have an explicit base on our log, it's assumed that it's 10. So, in other words, a logarithmic function is the inverse of an exponential function. When you use your graphing calculator, you can sketch out these two graphs. If you don't have a graphing calculator, go to Desmos.com. Okay, so the inverse of log of x, the function of log of x, is the function of 10 to the x. So whenever we graph these functions, they look a little something like this. Inverses, if you remember, basically just mean that our function has been reflected over the y equals x line. Okay. Because you can only graph base 10 logs on your calculator, you will need to use the inverse exponential function, then invert those values from the table to graph the logarithmic function. So I'm going to show you guys how to do that, what that means, and then I'm going to teach you how to use Desmos to kind of graph these out and talk about some key characteristics of log functions. All right, so first we have the function log base 2 of x. The first thing I have to do is I have to find the inverse function, which is f of x equals 2 to the x. All I did was I translated it from a log to an exponential function. Then I build out the values of my table. If you have Desmos and you don't have a graphing calculator, you can hit the little gear on Desmos and you'll see a little function for table, little option for you to build out the table, and then you have to actually input the values. So for the x, start at -2 and then go all the way to +2. And we just build out our table here. Now to find the values of log base 2 of x, we just flip-flop the x and the y. Right, so that's just the inverse. To take the inverse of that, we just flip-flop the x and y, then we plot our points. This image has come right from Desmos, so hopefully your Desmos image looks like this if you were able to figure out log base 2 of x, what that looks like. Let's start talking about some key characteristics. The domain. The domain is all the x values. X ends or gets really, really close to 0, but it never ever touches. So the domain is every value of x greater than 0. The range is all the y values. Our function goes from -infinity all the way to +infinity. So you can say all real numbers, or you can list it as set notation as I have right here. End behavior. We always talk about what our function looks like whenever we can't see it. Obviously, this picture only shows from -5 to +8. So what I want to know is what happens to x as y goes to +infinity. Well, x also goes to +infinity. Same thing as as y goes to -infinity, x approaches 0 and never ever touches. It gets really close to 0 but never touches. We can identify what the x-intercept is. It's pretty easy from the table. You look where y equals 0, or if you are not very good at remembering that's where y equals 0, you can just look at the function here, and it is the point 1, 0. The asymptote, again, we've been talking about asymptotes for a while. It is the line, the imaginary line that our function gets really, really close to but never touches. This happens to be x equals 0. I want you guys to remember that this is a line. Okay, so that's why we have an equal sign there. X equals 0. All right. Number 2. Number 2 is very similar to number 1. So if you're feeling like you want to try this out on your own, you go for it. If you don't, then just don't pause the video and listen to me. Okay. So, but if you want to give this a try, hit pause and I will keep going. All right. Then I'll meet you up later. Okay. All right. Welcome back to those of you who tried this out. So for number 2, our steps. The first thing we do is we translate it from a log to an exponent. The exponent of log base 1/3 to the x, or of x, is 1/3 to the x. So we look to see what our values are around the origin, -2 to +2. We take the inverse of that, so we know what points we're plotting. And our function looks like this. Okay? The domain is all the x values greater than 0. The range is all real numbers. End behavior, as x approaches 0, y goes to positive infinity. As x goes to positive infinity, y is going to negative infinity. The x-intercept is where y equals 0. In our table, it's the point 1, 0. Or you can look to see on your graph, which it happens to be 1, 0. The asymptote is x equals 0. So hopefully those of you who tried this out, you got all those answers correct. All right, so here is an example where we have a transition. We have the function log base 4 of x minus 1. Now, from here, obviously, if you guys have access to the internet, you have access to Desmos. So I highly suggest you give that a try. When you go to Desmos, you're going to have to go to miscellaneous and look for log. To input that little 4 there, you're going to have to hit shift minus. That brings the cursor down. So you hit 4, parentheses, x minus 1. When you build out the table, the x values are going to be all over the place. I'm not really sure what yours will probably show, but it might not show what mine's showing right now. I chose the x values to be 1, starting at 1, 1.25, 1.75, 2, and 3. The reason I chose that is because of this undefined right here. This tells me a lot about my function. It tells me where my asymptote is going to be. I know that every value below 1 is going to be undefined. So that tells me that's where I want to start. Then I look to see where my function crosses the x-axis, and it crosses it 2. So I wanted to kind of see what couple points were in between 1 and 2. So that's why I chose 1.25 and 1.75. And I looked at 3. So I can kind of see what the shape of my function looks like. So whenever we graph this out, we can graph the x-intercept, which happens to be 1, 0. The key characteristics, again, the domain is all of the x values greater than our asymptote, which is 1. So the domain is every x value greater than 1. The range is all real numbers, or from negative infinity to positive infinity, all the y values from those. The end behavior. As x approaches positive infinity, y is approaching positive infinity. As x approaches 1, which is our asymptote line, y goes to negative infinity. The x-intercept, I've already said, is actually, I misspoke, is the point 2, 0. And our asymptote is x equals 1. So if we were to think about how this function moved, did it move up? Did it move down? Did it move left? Did it move right? Well, it actually moved right. If we recall the transitions or translations from exponents and from quadratics, whenever it's in the parentheses, that tells us where it moves left or right. And we have to go against our gut. When it's a minus, we're actually moving it to the right. We're not moving our function to the left. So the log base 4 of x minus 1 is a translation to the right by 1. All right, number 4, we have the function log base 3 of x minus 2. So the parentheses here are very, very important. When I inputted this function into Desmos, I put x in parentheses. This tells me that this -2 is a constant. It's all by itself. Now, if we recall what that means, we're going to actually kind of see it visually here in a second. Again, I look to see what first number was undefined on my table, and it happens to be 0. My function does not pass 0, so I don't have to put any points below 0. Then I chose 1, 3, 5, 7, and 9. The reason I chose 9 is because that is my x-intercept. I don't show that here on my chart, but or excuse me, on my graph, but I can see that from the table. Okay. So the domain, again, is all the x values greater than 0. The range is all real numbers because our function goes from negative infinity all the way to positive infinity. And behavior, as x goes to positive infinity, so does y. As x approaches 0, y is going to negative infinity. The x-intercept, pulling it from our table over here, is the coordinate point 9, 0, and the asymptote is x equals 0. Now let's think about this in terms of translations. Did I move my function up, down, left, or right? I actually moved it down. You can kind of tell that from the fact that my x-intercept is so high. So it's much higher than the functions we've been talking about recently. Okay. All right, number 5. Looks like there's a couple of translations here. So if you're using Desmos, what I want you to do is build out the table first, and let's look at the graph. So what I did was I changed 1/2 to 0.5. And I made sure that x plus 9 was in parentheses and plus 4. This kind of cuts off here just because there's not enough room image-wise on Desmos. So whenever I'm looking at this function, again, I look to see where my function starts to be undefined, where my y values are undefined. That's going to tell me my asymptote. So my function gets really, really, really close to -9, but it never touches it. I also wanted to see where x equals 0 because that is going to be my y-intercept. Another very important point is where y equals 0, which is at 7. Okay, so that's why I chose all those points that I chose. The domain is x greater than -9. Every point greater than -9. The range is all real numbers. As my function approaches -9, y is going to positive infinity. My function goes up. Then, as x goes to positive infinity, sorry, I apologize. As x goes to positive infinity, y is going down. It's going to eventually go towards negative infinity. The x-intercept is that coordinate point 7, 0. And the asymptote is x equals -9. So the transformations here, we moved our function to the left 9. We're adding 9 here to the x, where it's x plus 9, which means we are moving our function to the left by 9, and we moved it up by 4. All right, try number 6 on your own. You can hit pause on the video and work through it on your own. I highly suggest you give this a try. All right, welcome back. So what this function looks like, hopefully looks a little similar to what I have here. This is another way to build our function, our graph, what it looks like. We take our parent function around the origin, and then we talk about our translations. So the translations are that we moved it to the right by 2 and up by 1. So I have to add 2 to every x value. And then I also will be adding 1 to every y value. So if you have this table here to the right, you are good. You're good to go. I just wanted to show you guys something a little bit different of what it really means whenever we are translating it from to the right 2 and up 1. If you go by Desmos and you're going through the process of how I taught you before, that's perfectly fine. If you translated this function into an exponent and then did the inverse of that, those values, and then plotted it, awesome. You're doing great, okay? This is just a different way. So our graph looks a little something like this. This is a dotted line, which means that's my asymptote. The asymptote is x equals 2. The x-intercept is 2.2, 0. That's a coordinate point. As x approaches 2, y goes to negative infinity. As x goes to positive infinity, so does y. The range, again, is all real numbers. Hope you're sensing a theme here. And the domain is every x value greater than 2. Okay, so the domain and the asymptote, they have some very related information there. Okay, hopefully you're picking up on some trends. So this translation, again, is to the right by 2 and up by 1. All right, so on the practice problems, we talked to you guys about graphing natural logs. You're basically doing the exact same thing. I just want to kind of expose you to what the inverse of the natural log is. We kind of talked about this last week, but I think seeing the graphs really hammer it home. Okay, so we have number 5. The function f of x equals the natural log of x. To translate the natural log of x to a logarithmic function, remember the natural log is the same thing as log base e. So all I did here was I translated it into a log, and we're going back from everything that we've done up to this point in this video. Okay, so if you would prefer to make it an exponent, you go for it. And then you find those values around the origin, and then you flip-flop them because those are inverses of each other. Okay, if you prefer to put this into Desmos, that's also awesome. Okay, so we have log base e of x into Desmos. And this is what our function looks like. If we talk about the domain, it's every x value greater than 0. The range is all of the y values. Think about Mariah Carey's voice. From negative infinity to positive infinity. The x-intercept is the 0.10. The y-intercept, there isn't one. Our function does not cross the y-axis anywhere, ever. It doesn't do it, okay? So don't put 0, don't, you can put none, you can put null, nada, I don't care. Just do not put 0, because 0 is a value. This function, if we read the function from left to right, is always increasing. It's always increasing. The asymptote is the line x equals 0. And when we talk about end behavior, as x goes to positive infinity, our function y, or y of our function, is also approaching positive infinity. Now this next one's a little bit different from the notation that we've been talking about from the notes. As x goes towards negative infinity, y also approaches negative infinity. So, as in our notes before, as x approaches 0, y is going to be approaching negative infinity. We're talking about the same thing here, okay? All right. Number 6. So we have the function natural log of x minus 1. So we've got a translation here. Same thing. To translate it to a logarithmic function, we have log base e of x minus 1. If you prefer to put this into exponential function or exponential notation and then build out your points around the origin and then flip-flop them, again, you go for it. If you prefer to use Desmos, that's okay as well. Your function will look a little something like this. Okay, so we are talking about the domain. The domain is every x value greater than 1. The range is every value of y from negative infinity to positive infinity. The x-intercept, our function crosses at this point right here, which is 2, 0. The y-intercept is nothing. It does not ever, ever, ever touch the y-axis. And our function is always increasing. The asymptote is the line x equals 1. So we have shifted it over, it looks like, right? We've shifted it over to the right by 1. That's our translation. The end behavior, as x goes toward positive infinity, so does y. As x goes to negative infinity, then y also goes to negative infinity. So the translation here is we moved it to the right by 1. All right, give number 7 a try. All right, I want you guys to pause this and do your best. All right, and then I will see you in a second. All right. All right, welcome back. So hopefully you guys gave this a shot. You're reviewing everything I have written down here, and it looks like it matches up. All right, so we have the function f of x equals the natural log of x plus 3. That plus 3 is by itself. It is not a part of x. So that translation is going to be a vertical translation. To rewrite the natural log of x plus 3, we have log base e of x plus 3. The exponential function view of our log base e of x plus 3 is e to the x plus 3. All right. Whenever you plot this graph, it should look something like this. What I did with Desmos is I went ahead and just pressed on my x-intercept so I can see very clearly what that point is. So the domain is every x value greater than 0, because you probably looked at your table. Hopefully you looked at the table and you saw that every number, every negative number, including 0, all of those numbers are undefined. So that means that our domain is every x value greater than 0. The range is from negative infinity to positive infinity. The x-intercept, I have here is 0.051. It's that coordinate point. The y-intercept does not exist. Our function never crosses the y-axis. This function is always increasing, always, always increasing, because we read functions from left to right. The asymptote is x equals 0. And our end behavior, as x goes to positive infinity, so does y. As x goes to negative infinity, so does y. Don't pay any mind to that red box there. That was just human error. Okay? All right. Now it is your turn. Get to working. Okay? If you have questions, please let us know. Thank you.